Hello everybody, we are going to talk about polynomials today. I hope this is something you already seen, maybe in college or maybe high school, but we can talk about polynomials again and refresh our memory. So what are polynomials? Polynomials are just expressions that can be computed using standard arithmetic. So we'll talk about polynomials over a field. Yes? So if you don't know what a field is, just don't worry, we'll have another video talking about fields, but let's see what they are. So definition, a polynomial f over a field f of degree n is an expression of the form f of x, where x is what we call a variable or maybe indeterminate. That's a formal sum, a sub 0 plus a sub 1 times x times a sub 2 times x squared plus a sub n times x to the power of n, where a sub n is non-zero and all the a sub i's belong to the field f. Yeah? 0 less equal to n. So this type of thing is what we call a polynomial of degree n over the field f. The degree is the highest power that you see here as a power of x. And we say that it's over the field f because all the coefficients belong to the field f. Maybe for you to have an idea, a field is a set of numbers that satisfy certain properties. Say, you can think of R, the real numbers. You can also think of examples of fields. You can think of f as being R, the real numbers, maybe Q, maybe you know Q, that's the irrational numbers. You can think of C, like complex numbers. Yeah? Those are like the main examples, but we're going to explore different options for f. We're going to start talking about finite fields, which are very useful for us, and maybe some other things as well. So examples of polynomials. Well, think of p of x defined as 2 plus 2x squared. So this is a degree 2 polynomial, yeah, over the real numbers. We can say that the degree of p is 2, right? Because the maximum, the highest exponent that we see is 2. This particular p is said to belong to R of x. So this is the set of all polynomials with coefficients in R. Set of all polynomials with coefficients in the real numbers. Right? So we have our first example of a polynomial. Then maybe we can have a different one. Say q of x 2 minus 3x. In this case, degree of q equals 1 because the maximum power that we have here is a 1. Yeah, highest power is a 1. So we have a different polynomial, this time of degree 1. Obviously, the list of polynomials is infinite, right? Maybe we can think of f of x. Let's use a different field this time. 2i plus 3x plus 3 plus 3i times x to the 7th power minus 4i times x to the 10th. So in this fashion, what we see now is that the degree of f is actually 10. All right? Because the highest power that we see is 10. And what happens with f is now that the coefficients belong to complex numbers, because 2i is a complex number, 3 is also a complex number, 3 plus 3i and minus 4i, all these guys belong to C. So now f is a polynomial with coefficients in C and indeterminate x. Right? So we have 3 examples of polynomials, right? This notion of degree is very important for us. It ends up defining a very strong property for polynomials. So we'll just talk about the degree a little bit more. There's a relation between operations with polynomials and the degree, right? And this is very important. We need to talk about degree because it enables us to find a way of comparing, so to speak, sizes of polynomials, right? Say that we have p of x, 2 plus x minus x squared, and we have q of x, 3 minus x plus x squared. Naturally, we can add 2 polynomials. We have the notion of addition of polynomials. And this notion is what you imagine that it is. Now we add p and q by adding the coefficients term-wise. So in this example, the polynomial p plus q at x, how can we find this new polynomial? It's going to be p of x plus q of x. And that's simply adding the polynomial p to the polynomial q. Right? And when we do so, we do it power to power, now in a power-wise fashion. So the independent term, the one that has no x with it, gets added with the other one, right? So 2 plus 3 equals 5. And then what happens? We need to look at the linear term, x to the power of 1. So I have plus x minus x, that goes away. We can write this as 0x Plus now we have to look at the quadratic term. So minus x squared plus x squared equals 0 x squared. In this expression, we only have just 5. So what happened here is that we have a polynomial of degree 2. So the degree of b is 2. The degree of q is also 2. But what happened with the degree of p plus q? So if we take a look at who p plus q is the polynomial consisting of just the number 5. So the highest power of x that appears in this expression is x to the 0. So we can think of 5 multiplied by a 1. So if the highest degree that we see is 0, we have this phenomenon. We can add two polynomials and end up with a polynomial which is of degree strictly less than those that we sum. So what happened here is a raw example of a more regular phenomenon. So observation, the degree of the sum is equal or less than the maximum of the degrees. Yeah. So it can be less. The degree can come down under a sum, right? Of course, we can also subtract two polynomials, and it's done in the obvious fashion. For completeness, we can maybe say how do we add polynomials in a formal way. So we have it written down, and it's in this video, but it's like the obvious fashion. So for completeness, addition of polynomials. So say that you have a p of x, that's a polynomial of degree n with coefficients a sub I, x to the power of I, and you have q of x, that's a different polynomial of degree n this time, and coefficients b sub k, x to the power of k. And suppose that n is less or equal to n. So the degree of q is at least the degree of p. So what is polynomial p plus q at x? Well, it's easily defined. So if n is less or equal to m, what we can do is we can say this: p plus q at x can be written as a sum from I equal to 0 to n of the coefficients times x to the power of I, and then what we have left is the coefficients of the greater polynomial. So in this case, it's q, from n plus 1 to n. Right? So this is a definition of how we would add two polynomials of degrees n and m. This is more maybe cumbersome to write than to do. We can always have polynomials in a very natural fashion. So this behavior of degree is somewhat kind of complex, but there's another operation besides addition and subtraction that comes with multiplication. Right? Multiplication of polynomials. And this is also done in a very natural fashion. Let's take an example. Say p of x is 2 plus x minus x squared, and q of x is 1 minus x. What is p times q at x? Well, it is defined as you'll imagine it is. So p times q at x is defined as p of x times q of x. So 2 plus x minus x squared times y minus x. And this is done by using basically distribution and taking into account that powers behave in a very nice way. Right? Observation, x to the power of s times x to the power of r is x to the power of s times r. So what we have now is just the distributive law. 2 times 1 is 2. 2 times negative x is minus 2x. Then you have x. X times minus x is minus x squared. Minus x squared times 1 is minus x squared. And minus x squared times minus x is plus x cubed. So if you gather terms with the same powers, 2 minus x minus 2x squared plus x cubed. So what we have done is actually computed the polynomial p times q. That's what it is. And what happened here? What we see now is that the degree follows a very different behavior. P is a polynomial of degree 2. Q is a polynomial of degree 1. And p times q ended up being a polynomial of degree 3. Right? So what happens is, because of this rule for adding exponents, now the degree behaves taking the degrees and adding them up. So what's very important here if the degree of p equals to n and the degree of q equals to m, then the degree of the product equals to n plus n. Right? So some people say that it transforms multiplications into sums. Right? But we're not summing polynomials, we're just summing their degrees. So this is a very important thing to have in mind. Right? The behavior of the degree function in relation to addition and multiplication of polynomials, right? And we need to think of the degree as a function that somehow measures how big the polynomials are. This is a very vague statement. We need to have like the right frame for that thought. And one of the first things that we are going to exploit is that fact when F is a field, the degree function provides us with a form of division algorithm. That is, when we're talking about polynomials over a field, which is our case, because of the degree, we can divide polynomials, right? And this is a very important notion that's going to lead to very interesting consequences, and the basic steps can be covered within this video, right? So we're going to state the theorem, and we need some things before, so let P be a polynomial. Let P and Q belong to the same set of polynomials over the field F, such that the degree of P is at least the degree of Q, right? Then there exist polynomials A and B in the same set, polynomials, such that P of x can be described as A of x times Q of x plus B of x, with the following property that the degree of B is strictly less than the degree of Q, or B is equal to 0 polynomial. So in a way, what this theorem is saying that whenever we have two polynomials, right, we can try to re-express the polynomial with higher degree in terms of the lower degree polynomial. And this reminds us of division. Like, this resembles to the division algorithm that we learned in elementary school. This time, the degree, what does is measures how big this polynomial B is compared to Q. Here, Q is the divisor. A is the quotient, and B is the remainder. And under these conditions, A and B are unique. So there's just one set of polynomials satisfying this condition. We cannot find two different pairs of polynomials that re-express P, right? So we need to think of this theorem, this division theorem just as we did in high school or maybe in elementary school. This is a version of a well-studied subject at school. Right? Say you want to divide 12 between 5. So what you did is you tried to find a way of getting close to 12. So what you did was, okay, 2 times 5 is 10, and the remainder of this subtraction is 2. Since 2 is smaller than 5, then we're done. And this division algorithm, what it was trying to express was the fact that 12 can be written as 2 times 5 plus the remainder. So this is going to play the part of P, this is Q, and these are the only numbers that we have. This is going to play the role of A, and this is going to play the role of B. And the division algorithm ended because 2 is smaller than 5. We had a way of comparing numbers. The way of comparing polynomials is by the degree, right? So whenever this has lower degree than this, boom, that's it, we're finished. So maybe we can run an example of this thing, and so you get a handle of how it's done. So let's divide P of X. It's gonna be maybe x squared minus 2x plus 8, and let's try to divide it by q of x, x minus 1, right? So let's try to do this. So we need to emulate this same train of ideas that we had in high school. So long division works in the same way. Solution. So you write your polynomial q in an orderly fashion, descending powers, and you write q in the same way. So what you need to do is you need to get close to x squared this time. So what do you need? You need something to multiply x with. So maybe x times x, that's x squared. X times minus 1, that's minus x. We're done multiplying, now we look at the remainder. When we take this fraction, x squared minus x squared, that's 0x squared, so that vanishes. And now we're left with minus 2x minus x. So that's minus 2x plus x, that's minus x. Once we're done, we're going to take this down. And now we check. Can we still divide? Okay, so we compare the degree of this polynomial with the degree of this polynomial. So since minus x plus 8 has the same degree of x minus 1, we can still run this algorithm. Again, this is going to be kind of easy. Minus 1 times x, that's minus x. Minus 1 times minus 1, that's plus 1. And now we take the remainder. This is fraction. The x goes away. And then what we have is 8 minus 1, that's 7. And now, can we still run the algorithm? Okay, so we have to check. This one has degree 0. And this one has degree 1. this is a sign that we're going to finish this algorithm right there. And we have, what we see now is that we have everything we need. So here's the dividend, okay? This is the polynomial we want to divide. This is the divisor, x minus 1. This is the quotient, and this is the remainder. So what this is telling us is that x squared minus 2x plus 8 can be written as quotient times divisor plus the remainder. And in this case, this guy has degree 0, right? So this is how it works. Right? This is like very basic stuff. Of course, this can be, implemented in software. This is done like in very different ways. Maybe graphically, you can display numbers in a different fashion, but the algorithm is basically this. And this opens a few more ideas. Basically, what we need to do is we need to define when two polynomials divide each other, right? So we're going to go with that definition. We say that P divides Q, both polynomials are the same set of polynomials, if the remainder in the division, the long division of P by Q is 0. That is, P divides Q if and only if there exists A in the same set of polynomials such that P of x can be written as A of x times Q of x. And now things maybe get a little sketchy because polynomials have this division property in a set of polynomials that we fixed beforehand. So it's very important that we don't lose this, right? So the polynomial that takes Q to P has to live in the same set of polynomials as the dividend and the divisor, right? So maybe from the notation standpoint, P divides Q. This is sometimes written as P dividing Q, the long vertical line between them. So P divides Q, that's the way it's written. So what comes next is all the theory behind the division of polynomials. That's a very interesting topic, and it lends itself to lots of details, because until now we barely used any property of the field F. It turns out that sometimes a polynomial divides another polynomial within polynomials of coefficients in a certain field, but when we change the field, we might lose that property, right? So that's important for us. Keeping track of what the field does is going to be crucial for us, right? So what's next? We defined a long division. Till now, we have done an example. We have defined division of polynomials. And we need to state a theorem that relates both constructions. It relates the way of dividing along division and a certain thing that we're going to take a look at now. And this is maybe. So we are going to talk about roots of polynomials. And maybe we can state the definition and then play around a little bit with it and then make the connection with the division, right? So let f be a polynomial with coefficients in f. Say f of x is a sum, x of I, x to the power of I, with I ranging from 0 to n. Right? And let x naught be an element of the field, right? So we say that x naught is a root of f if and only if f evaluated at x naught equals to 0. So what is this? Well, it's just replacing x naught where you see x. Now that you have is a sum of x to the power of x sub I, x naught to the power of I, and I ranging from 0 to n. To do this calculation, all you need to do is multiply and add numbers in the field f, right? So this is the definition of being a root, right? From high school, you know how to find the roots of polynomials when their degree is low. We know how to find the roots if x has degree 1 or maybe has degree 2. But when the degree goes up, we don't have formulas to find all the roots of a polynomial. Maybe we can get by with some very special polynomials of low degree, but we don't have a solution in the general case. Finding roots is hard. Can be done with low degree, but then when the degree goes up, it's kind of untractable. Maybe we can do it using approximations, but the exact roots very hard to find. We have another way of looking at roots. Yeah, because we're going to relate roots to factors of a polynomial, right? So what we have now is what we call Euclid's theorem. So let P be a polynomial with coefficients in f, and x naught be an element of f, right? So then x naught is a root of P if and only if Q of x, defined as x minus x naught, divides P, right? So this is a characterization of roots in terms of the division algorithm. X naught is a root of P if and only if x minus x naught divides P. We also state this saying that Q is a factor of P. It's a linear factor of P. So this is another way of expressing that Q divides P. Q is a factor of P. And this is a very nice theorem. It relates the way P operates with x naught with what polynomial divides P as a whole, right? So this is a beautiful theorem, and this is not very complicated to prove. Maybe we can sketch proof. Right? So by the division algorithm, we know there exist unique A and B polynomials in f of x such that P of x can be written as A of x plus x minus x naught plus B of x, right? And one of the features of that theorem is that this guy has degree strictly less than this guy, since the degree of x minus x naught is 1 because of the highest degree here is 1, then the degree of B has to be 0. And this tells us that B is a constant, right? So this polynomial right here is actually a constant. The thing is, which constant? Right? So up to now, what we have is that P of x can be written as A of x plus x minus x naught plus a constant B. So now let's suppose x naught is a root for P. Since it is a root, P evaluated at x naught is actually 0. But evaluating P is evaluating this guy, which in turn is the same as evaluating this guy, right? So what we have now is A at x naught times x naught minus x naught plus B. This is obviously 0, so this term vanishes, and we get that B is 0, right? So we have seen that if x naught is a root, then B is 0, and since B is 0, then x minus x naught divides P. So we have the first implication. If x naught is a root, then x minus x0 divides P. And for the opposite direction, right? The opposite direction, say x minus x naught divides P, then P of x is written like this, and then obviously evaluating at x naught gives that P at x naught is actually A at x naught times x naught minus x naught, and this is obviously 0. So then x0 is a root for P. So having a root is the same as having a linear factor of a polynomial. This is extremely powerful, and we're going to use this a bunch of times, right? What comes next is not only exploiting ways of dividing polynomials, but also ways of understanding how polynomials define functions, right? And how can we use polynomials to our advantage when we want to, say, communicate a message. Among all functions that we can choose, polynomials are basically the simplest ones because they can be determined by their coefficients. And that's a finite set of coefficients. As opposed to other kind of functions which cannot be completely determined by a finite set of numbers. Polynomials behave very good, right? So this is the first part. We have talked about this theorem, which is very important. We're going to use this a number of times. It's good to have this kind of general knowledge of the equivalence between roots and divisors and linear factors. Maybe we can have a video talking about the role that plays, the role that the base field plays. We can surely have one of those. So maybe next time we're going to talk about division details when it comes to fields, polynomials that cannot be divided by other polynomials, and how do we use that to express more complex things, and maybe we can add some other videos about the use of polynomials, right? So I hope this video was of use for you. Maybe you're not remembering some of these properties. Of course, there's lots of literature on this topic, but as a fresh primer to these things again, I think this is it for now. Right, so let's see you in the next video, and I hope you have a good week. Goodbye.